For billions of years, the planets in our solar system have been doing their thing, following these familiar paths like some kind of cosmic clockwork we just take for granted. But what if I told you all that stability, it's just a delicate illusion, and that a change smaller than a single millimeter could throw the whole thing into absolute chaos? Well, that's the question at the heart of the cosmic mystery we're about to dive into.
So where does this wild idea come from? It all starts with a pretty profound experiment that really challenged everything we thought we knew about our solar system's stability. And let me tell you, it revealed a truth that is both fascinating and, honestly, a little unnerving.
And this is the central question, isn't it? I know, it sounds like something straight out of science fiction. But an experiment back in 2009 suggested we need to take this very, very seriously. So, what exactly did they find that completely shook our understanding of our cosmic home?
Okay, so picture this. Researchers took everything we know about our solar system and ran it forward 5 billion years in a computer simulation. And they did this over 2,000 times. The only thing they changed between each run was Mercury's starting orbit by an impossibly tiny amount. We're talking less than the width of a piece of paper. You'd expect the results to be almost identical every single time, right?
Yeah, well, they weren't. In a full 1% of those simulations, that tiny, minuscule nudge was enough to cause absolute catastrophe. Now, 1% might sound small, but in cosmic terms, that's huge. It confirmed that disaster wasn't just some theoretical possibility. It was a real, non-zero probability.
In those chaotic scenarios, Mercury's orbit just spiraled completely out of control. It could crash into Venus or get flung directly into the sun. And what's worse, in one of those simulations, this tiny disturbance created a domino effect that destabilized the entire inner solar system. And this wasn't a calculation error. It was us seeing a fundamental property of gravity in action.
So, what is this strange and powerful phenomenon? Well, physicists have a name for it, the n-body problem. And it's the fundamental reason we just can't perfectly predict the future.
Simply put, the n-body problem is what happens when you have 3 or more objects all pulling on each other with gravity. Think of it like a dance. We can perfectly choreograph the dance of 2 objects, but the second you add just one more partner, the whole dance becomes so complex it's analytically unsolvable.
With just 2 bodies, like the Earth and the Sun, the math is clean, it's elegant, it's completely predictable. But you add a 3rd body, let alone 8 planets and a star, and everything changes. There's no general formula, no single perfect solution. That neat predictability just vanishes.
To understand why this happens, we kind of have to peek behind the curtain at the math, and it all boils down to a very simple and, to be honest, very frustrating mathematical rule.
This is a fundamental rule in math. If you want to solve a puzzle, you need as many clues or equations as you have missing pieces, or what we call unknowns. In physics, those unknowns are things like a planet's exact position and its velocity at any given time.
Now here's the thing. Even a simple 2-body system starts with too many unknowns. But physicists have this clever trick up their sleeve. Instead of tracking each object individually, they track their motion relative to the system's shared center of gravity. This clever move reduces the number of unknowns just enough to make the whole system solvable. It's a really beautiful piece of mathematical footwork.
But when you add a 3rd body, that trick just doesn't work well enough anymore. Even after you account for the center of gravity, you're still left with more variables than you have equations. And that's why it's unsolvable. It's not just that it's super hard, it is mathematically impossible to find one single general formula that works for every case.
This unsolvable nature leads to a very specific kind of behavior, and it's one that physicists have a very specific word for. It's not random. It's something way more interesting: chaos.
And this is such a key distinction. A chaotic system isn't random. If you could start 2 systems with the exact same conditions, down to the last atom, they would evolve identically forever. It's deterministic. But the moment there's an infinitesimal difference in the starting point, like moving Mercury by less than a millimeter, the future outcomes can just split apart and become wildly different. This quote just nails the essence of a chaotic system. That tiny shove, that millimeter of difference, that's all it takes to make any long-term prediction basically impossible. All bets are truly off. So if these systems are fundamentally unsolvable, you've got to be asking, how on earth do we launch space probes with pinpoint accuracy to other planets? It seems like a total contradiction. But thankfully, we have ways to work around the chaos.
So we can't find one perfect general formula, but we can get incredibly close. We use these powerful supercomputers to run massive simulations, calculating the forces step by step. We approximate solutions with incredible accuracy. And we use a really clever simplification called the restricted three-body problem.
This is one of our most powerful tools. The idea is, if one of the three objects is so tiny that its own gravity barely affects the other two massive ones, you can essentially just ignore its pull. This simplifies the math enough to make really useful, highly accurate predictions about its path.
And we use this all the time. Think of an asteroid. Its gravity is basically nothing compared to the Earth and the Sun, so we can use the restricted three-body problem to track it. It's the same idea we use for planning the trajectory of a spacecraft or even studying a tiny planet orbiting a binary star system.
Which brings us back full circle to our home. After all this talk of chaos and collisions, what is the final verdict on our solar system's fate?
Well, you can breathe a sigh of relief. While perfect, long-term prediction is impossible, our best approximations and simulations show that our cosmic neighborhood is stable. At least for the next few 100 million years, the planets should stick to their paths, and we don't need to worry about Mercury going rogue. So yeah, our system is a quiet, predictable dance for now. But it's a dance that could be interrupted. If an outside object, say a rogue star flung out from another system, were to wander into our solar system, it would add a new, powerful gravitational partner to the mix. And in that case, well, you already know, all bets are off.